Okay, good morning. Today we close up the part on localization, and then if time allows, we will move on to the next and last topic for this course, which is going to be RFIDs. And depending on where we stop today, we then reschedule next week. So either we take half of next week lessons to close up the RFIDs, and then dedicate all the remaining part of the course to exercises, or we reschedule somehow the next steps, okay? So just to briefly wrap up what we have seen yesterday in terms of localization, we have classified different ways you can actually use to implement a localization system based on radio frequencies or sensor nodes, sensor networks. We have mentioned that you can actually, the main building blocks of any localization system is the technology which you are actually using to localize, then the type of signal which you're using to get out the localization information, and then what we will see today is the algorithm which is then used to actually get the positioning out of the information which you retrieve from the radio frequency signal. Okay, so the general pipeline is you have some anchor nodes which are placed in the environment and which you know the position of, so you know where they are basically. Then you have some tags which are mounted on the entities you have to localize. These tags exchange some kind of signal with the anchor nodes, and the system extracts from this signal some type of information which then the system uses to get the information on how far is the tag to each one of the anchor nodes. And then this information on the distances between the tag to be localized and the anchor nodes is then fed into the localization engine, okay, which then tells where the tag is. Okay, and we have mentioned that there are several building blocks you can use to, for example, implement the localization system using a specific technology, and you can actually use different signal types to extract the information on what is the distance between any 2 points in your localization system. Okay, we have mentioned some of these, let's say, full-fledged system, and the slides you see here is basically giving a very, very short and synthetic overview on the different systems which are available to localize and which are the respective, let's say, features in terms of accuracy and cost and such. Okay. So we have mentioned that basically the systems which are based on the so-called RSSI, so the systems which use basically the transmitted and received power to get the information out of the distance, okay, they are the best ones when you are concerned with the budget, so when you want really a system which costs few, which does not cost a lot. On the other way around, if you are more concerned with accuracy, so if you are more concerned on localization error, okay, you'd better go to other types of systems which, for example, use as a reference signal, not the received power, but the difference between the transmission time and the arrival time of the signal from the anchor to the tag, or vice versa. Okay? So to summarize, if you want to go through, let's say, if your target performance measure is accuracy or precision, you'd better go for systems based on time of arrival kind of localization, let's say, approaches, where again you just estimate the distance based on the difference in time between when the signal was transmitted with respect to when the signal is received, and this delta in time gives you an estimate of the distance between transmitter and receiver. And generally, these kind of systems are based on ultra-wideband, which is a specific technology used for communication. On the other way around, if you want to target, let's say, reasonable accuracy with a trade-off on price, so on cost, you'd better go with for systems which are based on RSSI, so which are based on power. Okay? And then we have mentioned yesterday that within all these systems based on RSSI, you may want to implement localization through a parametric approach or through a non-parametric approach. Parametric means that you recover or you extract the distance information based on a parametric model. So you assume that the power received goes behaves with a given law with respect to the distance traveled by the signal. In non-parametric models, which are also called fingerprinting-based model, you just site survey your environment and then you extract the information on the distance just by querying a database which you pre-filled beforehand. Okay? We have already mentioned yesterday that systems based on time of arrival may, let's say, have some problems in case where you have reflections of the signal, so where you don't have, let's say, line of sight between transmitter and receiver, because in that case, if you have reflection, your synchronization may somehow get lost. Okay, so let's say systems based on power are in general more robust than systems based on ultra-wideband or time of arrival, given that though they have a lower accuracy with respect to the previous ones. Okay, so we'll focus from now on systems which are based on RSSI measurements. And what we will do next is basically assuming that we have some type of information on the distance between the tag and the anchor nodes, how this information on the distance or multiple distances from this tag to multiple anchor nodes can be used to actually derive the position of the tag itself. Okay, so we will let's say focus on what is called trilateration processes or triangulation processes. Okay, so that's very easy. Let's start from the ideal case. Ideal case is basically the case where the module which extracts distance from power or distance from time of arrival differences is perfect. It means that it can estimate with zero error where the tag is with respect to all the anchors. So you know perfectly how far you are from all the anchor nodes which you see. Okay, that's the ideal case. So in this ideal case, that's very easy. The process of trilateration is very easy because basically you have, for example, like in this figure here, which you don't see though, you have basically these blue points here are anchor nodes, okay, whose position is known, so you know where they are. And then you want to localize this red point here in the middle. Again, assuming that the module which gives us the distances between this red point and all the three anchor nodes is perfect, meaning that the distances are without error, okay, you can very easily find out what the position of this point is as a function of the position of the three anchors, just by using, for example, Pythagoras theorem. Okay? So what you want to, let's say, enforce is that the distances between this red point here and all the three blue points, okay, they are equal to the measured distance, which is, let's say, spit out by the module which extract the distances from any kind of measure in the signal received. Okay, so basically, the DI's measures are what the localization system gives you, provided some kind of sample in terms of received power or time of arrival measured. Then you know where the anchors are, so the Xi's and Yi's are the positions of the anchors, so you know there. And what you want to enforce is that the distance from anchor I to the reference point, which is X star here, is exactly equal to the distance which is measured by the localization system. Okay? So in this equation here, the unknowns are x star and y star, so the position of the red point in the figure, and all the other terms which you find there are parameters. Xi's and yi's are the coordinates of the anchors, which are known by default, and di is the distance, which is again returned by the module, which given in input as input the received power strand or the difference in time of arrival tells you what the distance is. Okay. Then you can write down this kind of equation for all the anchor nodes which you have in your system. In case of ideal conditions, so in case these measures here, di's, are not noisy, so they're perfect, you just need 3 equations to localize one point, which means that you just need 3 anchor nodes to get the position of one point. Okay, and graphically, this means that basically, you don't see it here, but it's like saying that you are searching the position of this red point here, which is in the intersection between 3 circles whose radius, means centered around each one anchor, whose radius is the distance di which you are measuring with respect to that specific anchor. Okay, so there will be a circle around this blue point here, another circle here, and another circle here, and what you're looking for is basically the common intersection point, which is the red point of these 3 circles. Clear? Okay. So this kind of system looks nasty in the sense that it's you have squares here, so it's not as first look a linear system. Okay. However, under ideal condition, you can derive from this system. This is 3 equations because it's indexed in I, so you have 3 equations of this type, 1 for each anchor. Okay. So what you can show is that if you have this 3 equation system, you can get to an equivalent system just by, for example, subtracting the 3rd equation to the first one and to the second one. Okay. So you can get to an equivalent system, which is like this one, which is linear. Clear? So I have these 3 equations. Okay. I take the first equation and I've subtracted the first equation, the 3rd one. I take the second equation and I've subtracted the second equation, the 3rd one. And what I get is an equivalent system by linear algebra, okay, which after some tricks in maths, simplification and such, it turns out to be linear. So in the end, what you get under ideal conditions, so if di's are perfect, is that you can localize by solving actually the linear system of equation. And the linear system of equation is here, down here. Okay? So basically, just to be precise on this, parameters of this system are xi's and yi's, so x1, x2, y1 and y2. Parameters of this system are d1 and d2. Variables are x star and y star. Okay? So as you can see, all x stars and y stars, they don't have any exponents, so it's kind of linear system. Okay? So why this is important? Because this is easily solvable, let's say, through kind of standard techniques, which means that you can localize very quickly. Okay? Clear? Questions? Okay. Then it's kind of more convenient to rewrite this kind of system using matrix notation. Okay. So just by grouping up the coefficients, the parameters of the localization system and the variable vector there, and you can actually rewrite that kind of system in a more compact matrix-like notation. Okay. Example. So what is this? What does this system look like in a very, very real and stupid case? Suppose I have these 3 anchors. One is here, one is here, and one is here. These are the coordinates of the anchors, and this is the point I want to localize. This point is in position 0, 0.5. Okay? So just by using this, let's say, matrix notation of the linear system to get the position, what I get in this specific case is a very, very simple 2 by 2 system equation, which in matrix form is expressed like this here. Okay? And if you kind of solve it, okay, you get the position of the red point. I guess there is a mistake here, yes, because y star should be 0.5, not 1. Okay? Clear? Questions? So, in other words, the mechanical way to get localization once you have distances which are without error is basically to get out of your system, get out of your environment a linear system like one you see in this slide, put in the parameters which are anchors, coordinates, and measured distances in the system itself, okay? Solve the system through standard techniques, and what you get is basically the perfect position of the point you want to measure. Sorry, the point you want to localize. Clear? Questions? Are you familiar with matrix notation? Yes, no? Yes? Of course. Good. Okay. So what's the problem? The problem is that distances are not error-free, in the sense that if we look if you look at this system here, these parameters here, d1, d2, d3, d4, and d whatever, are not perfect, which means that the distance which you measure, or better, the distance which you extract from your measurement might not be the real one. Okay? Why not? Because the measures which you're using to get out the distance, they're noisy. So they are affected by some kind of noise. Example, if we look at the RSSI, model-based localization, so our reference measure is the received signal indicator to invert the propagation law and get the distance. What you can observe is that the distance which is split back by this model-based approach may be different even if the point does not move. So for example, if you look at the figure at the left-hand side here, what this figure is showing is the probability distribution function, so the probability to get a specific value of distance on several attempts. So this kind of graph can be obtained, for example, by having one point, one transmitter, and one receiver which are fixed in position. Okay, and it can be obtained, for example, just by probing, so transmitting, for example, 1 million of beacons from the transmitter to the receiver, and then for each of these beacons, invert the distance with respect to the received power. Okay, so find the distance with respect to received power, and then have a point in this graph here. So if the condition were ideal, meaning if extracting the distance from the RSSI, the received signal strength, would be perfect, okay, what would you expect to be this kind of picture here? Huh?
If the measurements are completely exact, then this should be delta.
Exactly. So it should be a delta function. So for example, if the receiver is 4 meters from the transmitter, I should see here a peak, a spike, 100% spike, okay, at 4 meters. It means that with probability 1, what I'm getting out the parametric localization model is the exact 4 meters distance. Okay? As you can see, in real condition, you have a kind of bell-shaped function, which is around the correct value, say 4 meters. Okay, but still, even if you don't move anything in your system, still your inversion of the parametric model distance received power may, kick in some errors. So you may have, for example, a non-null probability to measure to estimate the distance, which is 2 meters from the real one. 3 meters from the real one. Okay? So why is that? Because basically the received signal power, if you think for 1 second, does not only depend on the transmitted power. Okay? You are in a kind of free environment, you are in, in the air, out there, which means that depending on what is happening around you at the time you are taking your received signal indicator measure, some kind of noise or interference can actually affect your measure of received signal to received signal indicator. Which means that, to summarize, the received power does not depend only on the transmitted power, okay? Which is the underlying assumption of that model which I showed you yesterday. But some, external kind of noise factor can kick in. And as this noise increases, the more this noise increases, the more wide is this bell-shaped function, which means that the farther away you can be from the real value of distance which you have to measure. Clear? Is it a question? Do you have any questions? No questions. Good. And obviously, the shape of this PDF function, PDF, depends also on the level of emitted power. So what's the level of the power the transmitter is actually using to transmit your beacons or his beacons. Okay? The higher the power, the more skewed, so the more, let's say, narrow is this PDF, the lower the power, the larger the PDF. Because if the transmitted power is lower, the impact of any interference would be higher on the received signal indicator measure. Clear? Questions? Okay, so basically all this discussion to say that the DIs which we have used here, they're not the real ones. So they might not be the real ones. Actually, they're not even scalar values, but they are samples extracted from some kind of random distribution, which is exactly this PDF here. Questions? Okay. So what do we do? So basically, this means that our approach of the ideal case is no longer applicable, in a sense that there might be, let's say, it might be the case, or it is actually the case in real condition that the system which we have wrote down before is no longer solvable. So there's no solution to that system. Because, for example, you cannot see it here, but if the distance measures are noisy, it means that the 3 circles which are centered at each anchor, so this circle here, this circle here, and this circle here, do not even intersect in one single point, which means that the system is no longer solvable. There's no solution to that system. Okay? Clear? Questions? So what do you do then? The thing that you do is that since there's no single solution to this kind of problem, there's no, let's say, well-defined solution to this kind of problem, what you do is to solve a kind of different problem. So you don't want any longer to find the intersection point of these 3 circles, because it does not exist. So what you want to find is the position of a red point here, x star, y star, which is, let's say, as close as possible to the 3 circles, so through this, let's say, to the 3 circles which are centered in the 3 anchors which are actually using. Okay? Clear? So I don't have a single solution any longer, so I want to find an estimate, a suboptimal solution, such that this solution is as close as possible to the measures, the distance measure which you have retrieved through your parametric model. Clear? So basically, taking as reference the system we used before, so we can, in any case, write down the system as just like we did before. The difference here is that there's no single solution. So what you want to find is, take as a reference this same system, is to find x star and y star that minimize some kind of error function. Okay? And the error function, which is minimized in this case, is the, let's say, square error of the point x star and y star with respect to the reference distance measure which you are actually taking. So formally, you want to solve a different problem, which is to find x star and y star that minimizes the square error of this quantity here, which is a times x minus b, where a is this matrix here, and x is the variable vector here, x star, y star, and b is the vector at the right-hand side of the equals. Okay? So this is a formal way to say that I want to find an x star and y star which is as close as possible to a, let's say, solution to this kind of system. Okay? Clear? Are you familiar with this notation here, with the two subscript here? This is the norm 2 of this vector, which means that, actually this is a vector. That's a difference between two vectors, so it's a vector. Okay? And the norm of a vector is just basically the norm square of the vector is basically the product element-wise of the vector for itself. So what comes out is basically, if you have, let me write down something here. So if you have one vector and you want the norm 2 of the vector, okay, so what you do is basically to do V times V transpose. T is the transpose of the vector, so what it comes out is that it's something like the sum of V1 to n of Vi squared. Okay, so you take each one element of the vector, you multiply by itself, and you sum up all the elements in the vector. So this norm, square norm to a vector just gives you the, let's say, the, how can I say it, the length of the vector. It's a measure of length of a vector. There are several, different norms which you can use, but this is the one which is most used in this kind of problems. Okay. Questions? Yes.
So do we use least square function here to minimize this?
This is exactly a least square function. That's exactly a least square problem. Okay. Least square is just you want to find the lowest. Let's say you want to minimize the square error of a given linear system like this one.
And here is the linear, right?
Yes.
Why is not
Why?
Why the function?
Because
it's related to distance. Non-linear function.
Yes, but you can. You were late, right? That's because you don't know. Because you can show that you can write down the localization system, so imposing the distance, let's say the measured distance equal to the formula of the distance, in such a way that it's linear in the unknowns. So you can do that, basically. Clear? So did you study least square problems somewhere else? No? Yes, no? Okay, that's very easy. So basically, again, we have this problem, which is a new one. We want to minimize some function here. Okay. What would be the value of this function in the ideal case? So suppose we are in the ideal case. Ideal meaning that these are all perfect. Okay. What would be the value of this function in that case?
The value of the function or the value of the solution, I mean x or x or...
That one is impossible to know unless I give you x's and these. The value of this function here. Zero, right? So in the ideal case, the distance between point you're localizing and, let's say, the circles which are identified by the anchor nodes and the distance measures would be 0. Because you can find one point which is exactly lying on circles of all the anchors, which means that this is 0. Okay? So this is not ideal, which means that we expect to have here an error function which is non-zero, which is higher than 0. Okay? But still we want to minimize it, so we want to keep it as low as possible. That's the only thing we can do actually. Okay? So just very quickly on how to solve these kind of problems, there are two ways. The first one is by resorting to some kind of, it's called normal equation, linear algebra. So you just take the matrix expression of the function you want to minimize, okay? You write it, you, let's say, explode it in its components, okay? And then you do what you would do in case of scalar equations or scalar function. So basically you take the derivative of this function you want to minimize and you enforce this derivative to be 0. Okay? If you do that, you're sure that the point you get out of this equation is a steady point, is either a maximum or a minimum. Clear? So just I just skip the details of linear algebra. So what it comes out is that basically to find the solution which minimizes this least square error function, okay, what you have to do in the end is to solve this kind of system. This is again a linear system. X is the, what do you call it, unknowns, vector, and all the other stuff are given. So it all scales down to solving again a linear system. This system, though, is, let's say, proven to have a solution, which is basically the least square solution of the original problem. Clear? Questions? And this is called normal equation. It's one of the fundamental equations in linear algebra. Okay? If you're familiar with MATLAB, you can, let's say, squeeze down all this process just by writing down one line of code, a 5 ASCII character code, which is, if you want to find out the position of a node, vector x, you just do x equal a\b. And you get the least square solution of the original system, which is in our case the position of the node itself. Okay? Clear? Questions? So, this is just to say that in any case, ideal or non-ideal case, solving a localization problem, so solving a trilateration problem, scales down to solving a linear system of equations. Okay. In the ideal case, the solution you get is actually the perfect one, meaning the real position of the node. In the non-ideal case, the solution you get is the least square solution of the system, which means that it's the solution which is the closest to the optimum which you can find out. Clear? Okay, so this is one way of solving these kind of problems. There is actually another very famous and used way to actually get the same solution. So to solve for the minimum of this cost function, okay, which is using some kind of learning algorithm, okay, like gradient descent. Have you heard about gradient descent before? No? Yes? No? So gradient descent is basically one of the fundamental algorithms in the field of, let's say, machine learning or algorithm in general. And let's say the sketch of this algorithm is very, very simple and stupid. So you have some function. For example, in this case, you have a function in R2 with two variables, which is f, x, and y. And you want to find the minimum for this function. So you want to find x and y, which minimize your function, which is exactly our same problem, right? We had a function, and we wanted to minimize this function in the unknown vectors, the position of the node. Okay? So what gradient descent does is basically it's an iterative algorithm. So it's not, let's say, an optimal algorithm. It's an iterative algorithm which starts from a given point, x and y, chosen randomly, I would say, and then iterates to move this point as close as possible to the optimal point, which is the point x and y, which minimizes the value of the original objective function fx and y. Okay? And how to do that is basically starting from this as x and y, keep changing x and y such that any change or this change reduces the value of the function x and y. Okay? And then you have a loop here, and then you stop until hopefully you reach a global minimum. So until you reach the value of f, x, and y, which is the minimum one. Okay? I guess that these kind of concepts or steps have been seen by you in many other courses, right? No? Yes? No? Okay. So what's the step you do to reduce the cost function? Okay, it's very easy and stupid. So you are at one x and y point, okay, and what you do is just impose the new point for the next iteration to come out of these simple rules here, which is basically you take your current position x and y, okay, and you subtract to the current position a quantity which depends on the partial derivative of your objective function with respect to that specific variable. So the new x value here will be x minus the coefficient times the partial derivative of f, x and y with respect to x. Okay, so basically this means that you're following the slope of the function fxy with respect to the variable x. Okay? And then you do the same thing with the other variables or any other variable you have. You may have functions which are in Rn, so with n different variables. So you iterate, you have a new point, okay, and then you keep iterating until you have reached the minimum. Okay? This coefficient here is called learning rate, which tells you basically how far you move from the current point in every step. Okay, and it's kind of sensitivity parameter which somehow gives you the speed of convergence of your algorithm. Okay? Clear? Yes?
How should we choose the initial point to start this?
Okay, that's a very good question. How would you choose the initial point? How would you choose a given x and y? Is it an issue or not? Huh? Why not? Do you agree? Does everybody agree?
But if we choose it not right, we can get far from the global optimum.
That's the point. So it depends on what the function is.
Sorry, I think our function is convex, and when it's convex, then wherever we start, we get the optimum solution.
Okay, so correct. In our case, so if we look at these kind of functions here, okay, these functions are convex, which means that they are ball-shaped. So they are shaped like a cup. Okay. So in this case, you are right. It's not an issue how to choose the initial point because you have one single global minimum. Okay. However, gradient descent is a general algorithm, which means that you can actually apply it to also non-convex functions. So, for example, you might have functions which look like this. In R1, so this is x, this is f of x, and you might have functions which are like this, right? So where you actually start from gradient descent does have an impact on whether gradient descent converges or not. So ideally, if you start here, okay, you may get stuck in this local minimum. On the other way around, if you start here, okay, you may get to the global minimum which is there. So where you start have an impact. So what you do in these cases is just to randomize the starting point. So choose one starting point and check out where the minimum, in which minimum point you actually ended up. Then erase everything. Choose another starting point. Look out, watch out in which minimum you ended up, and compare the two values. And you go on like this just by randomizing on the initial point you have. Okay? Clear? So, and that's the case basically. So in our case, as I was saying, our function is convex, meaning it's shaped like this. This is in 1D. In our case, it's a 2D function. So you should just imagine in your mind a bowl-shaped kind of function. Okay. Just to check that this step here is fine. So remember that any step of the gradient descent should bring you closer to the global minimum. Okay. Suppose we start from this point here, 60. So here. Okay. And let's see what happens if you apply that step there. So if you are at 60 here, we take the partial derivative, which in this case is the derivative of the function f of x. And as you can see from the figure, this derivative is positive because the slope is positive. Okay, which means that if we start from 60, we have a positive factor here, which is multiplied by a negative coefficient. So basically, if we start from 60, the new x will be somewhere on the left, 60. So the step is correct, in the sense that we move closer to what do you call it? To the global minimum. Okay? Clear? Questions?
For example, if we choose alpha so large, then we oscillate and we converge.
That's true. So what he's saying is that alpha here may also have an impact on convergence, in the sense that if you choose it too, let's say, large, it may happen that, for example, you are here, okay, the partial derivative is positive, so you have to decrease your x, but if alpha is too large, you may jump here, okay. Here, derivative is negative, still alpha is large, which means that you jump there, up there, and you keep iterating to infinity, which means that usually alpha cannot be chosen too large. Okay, so the trade-off is if alpha is too large, the advantage is that convergence is faster, provided that it converges. Okay. However, it may not converge. If alpha is too low, is too short, is too little, okay, it usually converges. However, it may converge in several steps, so not so fast. Okay, clear? Questions? So in our case, so in the localization case, if you apply gradient descent with a decent value of alpha, so not so large value of alpha, you get the very same solution as the solution of the normal equation which you have seen before. Okay? So this is to say that if you apply gradient descent to localization problems, since the function you want to minimize is convex, you are sure to end up in the global optimum, which is the one you get by solving the least square problem, which we have defined before. Okay? Yes?
Least square function more reliable than gradient descent?
Define reliable.
It's with one try we reach to the answer, even it's computationally more expensive, but we finally reach to answer. And we
Let's say,
have the other problem that here we have.
let's say you don't have to worry about setting proper parameters like alpha in that case, because you don't have any learning parameter if you solve the normal equation. So in that case, yes, it's more, let's say, reliable. in practice, so in many practical cases, the reliability is the same. So provided that you choose the proper alpha, okay, you get comparable solution time if you apply normal equation, if you solve normal equation, or if you apply gradient descent. Because again, it all scales down on what's the shape of the function. So if the function is easy, so it's a convex function like this, gradient descent behaves extremely well, okay, in terms of processing time and such. Clear? Other questions? Okay, and this is basically gradient descent applied to our specific case. So what's the shape of the function we want to minimize in our case? And what is the update step in our case? So the function is basically the sum of the squares of the distance errors. So the first part here is basically the distance between the unknown point and any anchor. And the second part is the measured distance out of the samples. This term in the brackets is just the error which you allow to have with respect to the distance measured and the distance from the estimated position. Then you square the whole thing up, okay, and then you sum up all the errors which you have for all the measures you have. So this sum here goes from 1 to the number of the anchors, so to the number of the measures which you are taking. So you want the sum of all the measures you're taking, meaning the sum of all the anchors you're taking measure from, to be as low as possible. Okay? Then you have 1/2 here just to be more, let's say, efficient in the solution process, because when you just derive this quantity, you have a square there, which goes away with this 1/2. But it does not have any effect on the final solution. Okay? The update step is basically just by taking this function here and taking the partial derivative of that function with respect to the two unknowns, so with respect to x and y. Okay, this is the partial derivative if we derive that function with respect to x, and this is the partial derivative if you derive it with respect to y. Okay, so if you apply gradient descent, you just start from one point. Okay, measure these partial derivatives in that point, and then choose the next point, x and y, just by subtracting the current point these two factors, which are alpha times this partial derivative and alpha times this other partial derivative. Okay? Clear? Questions? Okay. And this is the shape of our function. So it's kind of, let's say, template shape for the error function in terms of localization. In the field, I would say, in the field of localization. Okay? And that's why gradient descent always ends up in the deep of this function, so in the global minimum, this function here. All the localization systems which I'm aware of, I mean practical ones, are based on gradient descent or variation of gradient descent. Okay? No one that I know applies the solution of the normal equation. Okay? Questions? Okay, so if you don't have any question, we can move on to our next topic, which is going to be radio frequency identification. So basically, as a placeholder again, what we do next is to consider cases where sensor nodes are no longer active, meaning they are no longer equipped with batteries, which means that they are totally passive. This has a huge impact on both the hardware of these nodes and also on the communication protocols which you can use to get out information of these nodes. Why? Because you don't have batteries, which means that you cannot actually run on the node complex protocols like SMAX, PERMAC, 15.4 and such. More than that, you cannot, let's say, store in the node huge quantities of data. So you cannot have, for example, routing tables, RFIDs node in tags. And more than that, you have to have some kind of ways to provide power to these passive nodes. So they have no batteries on board, which means that they have to, when they have to run on external kind of power. So someone else has to provide power to these nodes such that they can actually send some kind of information back. Okay? So this RFID concept is basically the same concept of barcodes. You know what barcodes are, right? So what you find on items to identify what the item was or what the item is, which is that kind of black and white stripes on the item. Okay. That black and white stripe is, just contains an encoded version of an identifier for the specific item. So depending on how wide are the stripes and what's the, let's say, sequence of stripes you have, that kind of barcode identifies uniquely that specific item with respect to others. Okay? And what the RFID is doing is actually to translate this idea of barcode, okay, into an electronic barcode. So no longer a barcode which is scanned through some kind of optics or visual scanners, okay, just like at the supermarket when you check out your items, but rather a barcode which can be read through RF technology, so radio frequency technologies. Okay, that's why it's called radio frequency identification or radio frequency barcode. Okay. So the idea is to take this barcode, translate it into an electronic one, which can be somehow read through wireless transceivers, which are also called readers in the field of RFIDs. Okay? So as you can just imagine from this very, very brief introduction, we are not really talking about transferring information just like in active sensor network. So we're not talking about transferring, for example, temperature samples or pictures taken from visual sensor nodes or such. We are talking about identifying items, which means that the piece of information which is central in RFID is only, or mostly, I would say, the object identifier, the address of the object which is to be somehow identified. Okay, so just to set the scope. We are here talking about systems which are out there only to transfer from one tiny tag to some reader the identifier of that tag. So who the tag is, basically. Okay, so the kind of systems with very, very low ambitions in terms of traffic. Okay, just to set the scope. But still, to realize this kind of system, it's not, let's say, so easy because there are some challenges which should be accounted for. Let me just skip this background here to get to the building blocks of RFIDs. So basically, as I was anticipating, we have two main building blocks, actually three main building blocks of an RFID system. Let's talk about the front end. So basically, the devices which are used to manage the communication part only. Okay. So in that front end there, you have two main components. The first one is the tag on the right hand side there. So basically, the tag is a electronic circuit which has some kind of radio frequency module or transceiver. Okay. And it also may contain some additional components some of which we already found in active sensors. For example, we might have some kind of memory, local memory, much more limited than the one in active sensor networks. We might have some very, very simple control logic to manage the protocols to, let's say, transfer information. And what is important, this kind of circuit here is based on battery scavenging or energy scavenging, which means that the circuit is not powered up by local energy, but should be powered up by energy coming from abroad, coming from somewhere else, which is called energy scavenging or battery scavenging. Okay, so one component of this tag is an electronic circuit which is used to provide energy to the tag itself, taking it from outside. We'll see in 1 second how. Okay? Then, depending on what kind of target design you have here, you might have also sensors and processing units, but let's say the standard tags are basically composed of this circuit, which is handling scavenging and transmission, and a very, very tiny memory to store locally the ID of the tag itself. Okay, that's it. Then you have the reader, which is the other part of the picture. The reader is basically the tool which is used to get out the ID from the tag. The reader is basically a, let's say, PC, I would say. So it can be seen as a very, very powerful device, just like a PC, and has all the features of a, a given a classical PC. So it can be, for example, it does have a processing unit, it does have much more memory than tags, it may be connected to power supply, it may have external connectivity like Wi-Fi modules, 3G modules or whatever to get out information, to transfer the information obtained from the tags somewhere in the internet and so on and so forth. So it's a kind of higher layer device with respect to the very, very simple and naive device which are the tags. Okay? Clear? So one thing which is not an hardware component but rather a logic component is the so-called arbitration mechanism or arbitration protocol, which should reside somehow both in the tags and in the reader, which means that the tag should be able also to run a very, very simple arbitration protocol. What is arbitration protocol? It's basically the equivalent of a medium access control protocol in active networks. Arbitration means that typically when the reader wants to read a bunch of tags, meaning when the reader wants to identify a bunch of tags, okay, he does it through one single command. So the reader just does click, okay, and then automatically all the tags which are in the range of the reader, they will answer with their ID. Okay, that's the common process. The problem of this process is that you have multiple tags which might answer at the same time, which means that you might have collisions at the reader. Okay? So to avoid this collision, as we will see, there are several arbitration mechanisms which are basically mechanisms to handle multiple transmission, concurrent multiple transmission from the tags to the reader, such that the reader is able to identify all of them. Okay? Clear? So you should expect to find in the tags also a very, very simple logic to implement this kind of medium access control or arbitration protocols. Okay? Okay. To be 100% precise, there are not only RFID passive tags, but you can also find semi-passive tags or active tags. Active tags actually are similar to what we have done so far, so are similar to what we have called so far sensor nodes, sensor networks. They have batteries, they have several kind of capabilities in terms of processing, transmission, and so on and so forth. Let's say 80% of RFID tags are passive. Then you have some tags which are semi-passive, which means that they are, let's say, triggered by external energy. So they are triggered by some kind of external signal, okay? But still they have onboard batteries to handle specific process procedures. An example of these semi-passive tags is telepass. I don't know if you know what telepass is. You know what telepass is, right? Yes, Italian guys for sure know it. So it's this kind of stuff which you mount on your car, in your vehicle, to automatically pay the tolls at toll booths here in Italy. So if you open up this box here, half of the box or 3/4 of the box is composed of a battery, and the 1/4 is a semi-passive RFID tag, okay, which is basically excited, triggered when you get close to the toll booth, by signal which is received from the toll booth, is activated by this signal, and then it uses the local battery to, speed up some kind of power or signal to the toll booth stuff or machinery. Okay? Clear? Okay. So, which are the applications? I guess that you all have in mind what kind of application you can actually do with RFIDs, which are spread in different fields. Okay, starting from warehouses where you want to control, for example, shipment of goods, of items, or for example, you may want to attach RFIDs to people or animals, just to track them. Okay, this thing here, this Polyme card, is an RFID card. Okay, when I get to office, I just swipe the card close to the reader. Okay, and the reader identifies who I am, if I was late, if I was early, and which does not happen so often. Let's say it's more likely that I'm late. But still, it's an RFID tag, in the sense that in here you have a very, very stupid and simple circuit which is excited by the reader, so the thing you swipe the card close, and then gets back my ID, basically. Okay? So you can give RFIDs to people, just like this one. You can apply RFIDs to, for example, goods in supermarkets to avoid robberies. Okay? The so-called, what do you call it? I can't find the name. So when you get out of the shop, there are usually these barriers, which are, I don't know what's the name in English. What's the English name? Anyway, you got it, right? So if you exit through these barriers with a good, with a tag already still on it, these things, makes crazy sounds, okay? And that's an RFID application, because you attach one tag to an item, okay, to, let's say, implement some kind of anti-theft or anti-robbery kind of services. So you can basically attach RFID tags to whatever goods you want, and depending on where you attach these RFID tags, you implement different services. Okay. So that's a very, very generic architecture for a tag. Let's say most of this design is taken by the RF part, radio frequency part, which is composed of an integrated antenna and a circuit which is activated by external power. Again, we will see in 1 second how this circuit is excited or triggered. Then you have some receiving logic, which is receiving the signal out of the RF part. You have some memory, and you have this protocol engine. Protocol engine is where the collision arbitration mechanism is actually implemented. Okay? Just like for IP addresses, I would like to say, or just like MAC addresses, also the format of IDs which are stored in RFID systems is somehow, I would say, semi-standard. So it's standardized, let's say. And the reference format of these IDs is called EPC, which stands for Electronic Product Code, which again specifies a format of what can be stored or what should be stored in any RFID device. Okay, I'm not interested in the specific details on what this ID looks like. The message is that it's very similar to a MAC address, so to an hardware address, because just by looking at this EPC, you can identify who is the owner of the tag, what kind of, let's say, service the tag is attached to, warehouse, health, or other kind of services, and then other specific information on the specific duty of that specific tag. So again, it's an address which is hierarchical, it's split in different parts, and each part of this address gives you information on what the specific tag is. It's the owner, and so on and so forth. Okay? Again, not interested in detail. So, which are the challenges to implement this kind of system? The first one is energy scavenging. So we want to do all this identification process by using passive hardware, which means that it really wants to extract energy from the environment. Second one is, let's say, I would say an implementation challenge, in the sense that you really want to make this tag as little as possible, depending on where you want to store them, okay, in a credit card, for example. And the third one is cost, in the sense that these RFID systems are usually deployed on very huge scales in terms of number of tags, okay, which have to be deployed, which means that it's not affordable to have tags which cost too much. Okay, the reference price here is around, let's say, few cents of euro, few cents of dollar per tag. Okay, otherwise it's not, let's say, affordable from the market point of view. On the reader side, there's not many implementation challenges, because the reader is a kind of device which have fewer constraints than the tags, so it can be power operated and such. The only challenge, or the only thing which you should account for when designing or using readers, is how to interface your reader to the backend, so what is called backend. Okay, for example, the database which is storing all the IDs which are read, or the backend of the specific implementation service which is then accessing some kind of information in the internet. So all the challenges which are specific to the reader deals with how the reader can actually transfer the information out the RFID system into the internet or into the backend. But that's more, let's say, classical and well-solved challenges in also many other fields. Okay, so the real problem is the front end. Okay, between the reader and the tags, not really the other way around. Okay. Let me just skip some slides. These are only examples of RFID's applications, so where you can actually place readers to read something. Okay, the reader can be handheld, so it can be a mobile device, for example. Like in this case, there's a person who goes around and just scans different pallets of products, different bunches of products. They can be mounted on conveyor belts, so there is goods which are going through a conveyor belt, and then you have a reader, and as the goods gets close to the reader reads the good, and so on and so forth. They can be placed on shelves in supermarkets, or they can be placed in vending machines, for example, just to monitor when one specific item is missing or not. Okay. And there's also one huge application field, which is the one of point of sales, which means that readers are also all those devices which can be used to pay in a contactless way. So when you go to some place, you want to pay something, you just swipe your credit card. You don't have to give the credit card to the guy, you just swipe the credit card on this kind of point of sales reader, and then the transaction, the money transaction, happens without any contact between yourself and vendor, let's say. Okay, so this is another example of RFID solutions. Okay, questions? Okay, so let's see basically more in details the technology. So how can we implement these passive transmission systems and what kind of challenges we have. So let's start from the frequencies. What you see in the picture is basically a map of frequencies which can be used to implement RFID systems. Okay, they are divided into low frequency, high frequency, very high frequency, ultra high frequency, and so on and so forth. Okay, and each one of the specific frequency band has specific features in terms of, let's say, I would say two performance measures. The first one is what can you do in that frequency range, meaning what range can you achieve in that frequency range, meaning how far can you go from the reader to the tag in the specific frequency range. And the second one is the specific technique which you use to scavenge energy if you run an RFID system in one specific range. Okay? So if we are talking about low frequencies or high frequencies, meaning up to tens of megahertz, okay, usually the technique which is used to scavenge energy, so to provide energy to the tags, is called magnetic coupling. Just to anticipate, this means that the tag gets energy out of the magnetic field which is generated by the reader. Okay? We'll see in 1 second what this means. If we go up in very high frequency or ultra high frequencies, okay, the technique used to scavenge energy is called electromagnetic coupling, which means that the energy is obtained from both components of the field, so from the electric and the magnetic component of the field, which is generated by the reader itself. Okay? I would say that most of the RFID system use frequencies which are around here, so 800 megahertz, which is, if you think, the same frequency which is, or one of the same frequencies which are used by 15.4. Okay, sub-giga frequencies of 15.4. Okay. Okay, so let's talk about these two models for scavenging energy. So we have mentioned two coupling models, so two ways to scavenge energy. The first one is magnetic coupling, which is also known as near-field coupling. And the other one is electromagnetic coupling, which is also known as far-field coupling. Okay? So let's start from near-field coupling or magnetic coupling. The idea is the following. You have a reader which transmits some kind of signal, okay, wireless signal. This signal is an electromagnetic wave, okay, which propagates in the environment, and the tag here, or better, the receiving circuit of the tag is shaped as a coil. You know what a coil is? A spirale, okay. And as you should know from your physics courses, okay, whenever you have a magnetic field which goes through a coil, through the spirals of the coil, okay, this magnetic field generates a current in the coil, which somehow gets power to the tag itself. Okay? So, just to be very synthetic in this way, the idea is the reader generates a magnetic field, and this magnetic field excites the coil, which is at the receiver side of the tag, and which generates a current in the coil itself, which is then connected to the backend RF system. So the current is conveyed to the backend system, which is powered up by this current. Okay. Then the backend system can backscatter any kind of signal using this current which is generated by the reader itself. Okay? Clear? The principle of far-field coupling, which is electromagnetic coupling, is more or less the same. The difference is that in electromagnetic coupling, we are using also the electric component of the field. So we're not using only the magnetic field, we're also using the electric component of the field. Okay? This means that the type of receiving circuitry at the tag is slightly different. It's no longer a coil. Okay, it's something, let's say, more refined. But still, the effect and principle is the same. So you have an electromagnetic field which excites the receiving circuitry of the tag, which generates a current, which is then used to power up all the back end of the tag itself. Okay? What's the difference? So why using one or the other one? It depends on what you want to do. Usually, inductive coupling here, it's more effective at lower frequencies, which means that the current which is generated here at the tag is, let's say the current level is higher if the frequency of the signal is lower. Okay. However, to get a good coupling, to get a good current level here, the distance between the reader and the tag cannot be high, which means that it must be below 1 meter, roughly. So that's why this kind of coupling is used in all those applications which require some kind of low distances between reader and client. For example, this is the case which I made before, like using my card, swiping my card on a reader, because the card is very close to the reader, so I can actually use magnetic coupling. Okay. Vice versa, if I can actually use both components, I have more flexibility on the distance between tag and reader. Okay. And usually this is better, or the quality and the level of the current which is generated in the tag is much better under electromagnetic coupling at higher frequencies. Okay. For example, sub-giga or even above a gigahertz frequency. Clear? Question? So we are not going into the electronics detail on how the circuitry are shaped. What I want you to understand is that the principle is very easy. I, in one case, extract current from the magnetic part of the field. In the other case, I extract the current from the electromagnetic part of the field. Okay? I can do this if I'm close to the reader. Okay? I usually do this if I'm far from the reader. Okay? Okay. So, and this is the reason why I cannot do actually magnetic coupling with large distances. Because basically, it can be shown that the range between transmitter and receiver, in order to have enough current to the receiver, okay, must be comparable to the diameter of the coil. So it must be comparable to what is the diameter of the antenna which is used to generate the field itself. Okay, and that's why I cannot have coils which are hundreds meter, because otherwise I should have a reader. I would have a reader which is 100 meter long. Okay, that's why I have to keep this range very short. Okay, that's just a technical detail. In the electromagnetic coupling, as I was saying, we are more flexible in the range, in the sense that the range basically depends on how much power we are putting in the electromagnetic field. Okay, and there are different laws which tells you what's the maximum range you can have, such that generated current is enough for letting the tag working, and these curves, these laws, depends on the frequency we are in. So if you look at the graph on the right hand side here, this is telling you, given a limited power for the reader, what's the average maximum range you can get out of that specific transmitted power for two different frequencies. This is 800 and something gigahertz, and this is 2.45 gigahertz. Okay, so as you can see, the more power you put on the receiver, sorry, on the transmitter, okay, which is the reader, the higher the transmission range. The higher the transmission range, yes, or the reading range, and the reading range increases also if you lower down the frequency. So if you are using lower frequency, you will get more far away, basically. Okay. And the low, which is below these curves here, is the one you see at the left-hand side here. This tells you what's the Rmax, provided that you have different values for the transmitted power and such. Okay. One very quick observation on this issue. Just have a look at this picture here, which is representing the antenna at the reader side and what happens at the tag side here. Okay? So if you look at this antenna here at the reader side, you have, for example, an outgoing power going from the reader to the tag, which is 0.5 watts, so 500 milliwatts. Okay? Then this power, depending on how far the reader is from the tag, may get down to few microwatts at the tag. The tag then does what we have said before, so it gets current out of this electromagnetic field and then generates back a signal which goes out with a power of, again, few microwatts. And this signal here gets back to the reader with a level which is in the fields of picowatts. Okay? So why this is a problem? This is a problem because it means that this antenna at the reader side must be able to distinguish, let's say, signals in the range from 500 milliwatts down to 100 picowatts. It means that it must be an antenna which is highly sensitive. Okay? Which means that there is also a challenge, which is already solved though, in designing antenna at the reader side of such features. Because usually one antenna is, let's say, highly customized in terms of what's the sensitivity range it has. And usually an antenna is, let's say, specifically designed to, let's say, receive power in a very in much shorter range than this one. Okay. Here we're talking about order of magnitudes of received power range for this antenna, which means that also this antenna design must be, let's say, carefully taken care of. Okay? Clear? And the other comment is that since we are receiving such low power from one tag, we are really concerned about interference. So the signal which is received back to the reader from the tag is very low, which means that also the interference must be very low. Otherwise, all the process of arbitration, so identification of the tag, can be somehow impaired. Okay? Questions? Questions? No questions? So, which band to choose? What kind of technology to choose? Again, it depends on a specific application. So it depends on the specific application field. Usually, as I was saying, most of the RFID systems are in the ultra high frequency range, so in the field of hundreds of megahertz, so from 400 megahertz up to 800 megahertz and so on and so forth. Okay? There are still some applications in the sub-giga, in the low frequency domain, but there are more related to point of sale or contactless payment kind of application, where you just need to have, very short distances between reader and tag, also for a security reason. So you don't really want to pay your bill, or you don't really want to allow the system to charge you your bill when you are, 100 meters from the cashier. Okay, you want to go there, see how they are billing you and then just contactlessly pay your bill, but having a feedback on the bill is actually paid and the amount of money you paid is correct. Okay. Questions? Okay, so if you don't have any questions, I would stop here, because what we have still to do on RFID is to talk about RFID collision arbitration. So assuming that we now know how one single tag can answer back to the reader what is its own ID, using these techniques of coupling, we still have to answer to the question on how to resolve multiple tags which are answering at the same time to one single reader request, which is called collision arbitration or arbitration mechanism. And this is something we will do, I guess, next week right now. Okay? So just to wrap up, next week we will have, we'll close up the part on RFIDs, and we will take all the remaining time for next week for doing exercises. So it can be, for example, second half of Wednesday class plus all the Thursday class, and then we will see what happens for the week after the next one. Maybe we can schedule another couple of exercise sessions in preparation of the exam dates. Okay? Okay, I'll see you next week.
Is anti-shoplifting.
Say again?
It's anti-shoplifting device. The name of the device that's are in the store is anti-shoplifting.
Sì?
Può chiarirmi un dubbio. Io dai corsi di fisica ho sempre intuito che con le frequenze più basse era più facile raggiungere distanze maggiori per via del fatto che le frequenze più alte sono più soggette non so, a fenomeni atmosferici, tipo anche la pioggia, magari le alte frequenze ne risentono, le basse no.